Hello, viewers. Welcome to my channel. In today's live, we will be reading Chapter 8 Measurement of Time and Motion, taken from the Curiosity Book of Science, Class 7. As the screen is clear to you, so let's begin with the reading of Chapter 8 from the Curiosity Book. In case you are interested in hearing the audio of first 7 chapters, you can come to the playlist of my channel. Predna and her younger sister are watching a sports channel on television. Predna enjoys running and she has been declared the fastest runner among the girls in her district for winning the 100-meter sprint at an inter-school competition held at the district level. She is now training to compete at the state level. She dreams of representing India at the international level in 100-meter sprint contest in future. While watching the rerun of sprints at the Olympic Games held in the past, Prerna is always amazed that the measurement of the time taken for the race is so advanced that they could identify the winner even when two sprinters seem to cross the finish line almost together. However, in her school, the sports teacher only used a special kind of watch called a stopwatch for timing the school races. She had noticed her mother wearing a watch on her wrist and her sister looking at her mobile phone when she needed to check the time. Her uncle used a braille watch and had recently acquired a talking watch that announced the time at the touch of a button. There was also a large clock on the wall near the school entrance. Her thoughts turned to people in the ancient past who did not have the modern gadgets we have today, and she wondered. I hope this screen is clear to everybody. The earlier screen was tilted a bit. Measurement of time. Humans got interested in keeping track of time long ago. They started noticing that many events in nature repeat themselves after definite intervals of time. For example, the rising and setting of the sun, the phases of the moon, and the changing seasons. They started using the cycles of these events for timekeeping. First, they devised calendars. A day was defined by the cycle of rising and setting of the sun. Then began the quest to find ways of knowing the time of day. So they made many devices which helped them to measure smaller intervals of time within a day. Some of these were sundials, water clocks, hourglasses, and candle clocks. In a sundial, time is determined with the changing position of the shadow of the object cast by the light of the sun during the day. So this is a sundial. In this figure, you can see this is a water clock, and in B, floating bowl type. In 8.3, this is an hourglass, and this is a candle clock. So we will be discussing one by one. In a sundial, time is determined with the changing position of the shadow of an object cast by the light of the sun during the day. The water clocks use the flow of water out or into a vessel to measure time. In one type, water flowed out from the vessel which had markings for time. In the other type, there would be a bowl with a fine hole at the bottom, which was floated on the surface of water. It gradually filled up in a fixed time and finally sank. Then it was lifted up and floated again. In an hourglass, time was measured on the basis of the flow of sand from one bulb to another. Candle clocks were candles with markings that indicated the passage of time when burnt. Fascinating facts. The world's largest stone sundial, the Samrat Yantra, was built around 300 years ago at the Jantar Mantar in Jaipur, Rajasthan, a UNESCO World Heritage Site that houses several astronomical instruments. With its imposing height of 27 meters, its shadow moves at about 1 millimeter per second and falls on a scale finally marked to measure time intervals as short as 2 seconds. Like any sundial, it measures local or solar time, requiring a correction to determine Indian Standard Time. Should we make a simple water clock? Activity 8.1, let us construct. Take a used transparent plastic bottle, half liter or larger, with its cap. Cut into two, roughly in the middle as shown in figure 8.5a. Using a drawing pin, make a small hole in the cap of the bottle. Place the upper part of the bottle in an inverted position over the lower half. Fill the upper part of the bottle with water. You may add few drops of ink or color to make the water level easily visible. So whatever is written here has been depicted in this figure 8.5. The water will start dripping into the lower part of the bottle using a watch. Mark the level of the water after every 1 minute till all the water drips down. Your water clock is ready. Can you now guess how to use it? Pour the water from the lower part back into the top part and watch the level of the water dripping into the lower part. Every time it touches a mark made by you, one more minute has passed. Fascinating facts. In ancient India, time was measured using both shadows and water clocks. The earliest reference to shadow based time measurement appears in the Arthashastra by Kautilya, was composed and revised between the 2nd century BC, 3rd century CE. An accurate expression from time in terms of the shadow of a vertical stick was given by Varaha Mihira around 530 CE. The water clock with water flowing out was determined in the Arthashastra, Sardula Karna Vadana, and some other texts early CE centuries. These clocks were not very accurate because as water levels dropped, the flow rate decreased. This led to the development of the sinking bowl water clock, as shown in figure 8.2b, or Ghatika Yantra, first mentioned by Aryabhatta and then in several astronomical texts later. Time was measured constantly with Ghatika Yantra at Buddhist monasteries, royal palaces, town squares, and each time the bowl sank, it was announced by drums, conch shells, or striking a gong. Though the Ghatika Yantra was progressively replaced by the pendulum clocks in the late 19th century, it continued to be used at the religious places for rituals. A human civilization advanced, and as people began to travel long distances, the measurement of time became very critical. This led to the development of increasingly better mechanical devices for the measurement of time. Driven by weights, gears, and springs from the 14th century onwards. However, the invention of the pendulum clock in the 17th century marked a major breakthrough in mechanical timekeeping. Now, a scientist. The pendulum clock was invented in 1656 and patented in 1657 by Christian Huygens. He was inspired by the investigations of pendulums by Galileo Galilei. It is said that once, while sitting in a church, Galileo's attention was drawn to a lamp suspended from the ceiling, which was swinging back and forth. Using his pulse to measure time, Galileo found that the lamp took the same time for each swing. After experimenting with different pendulums, Galileo concluded that the time taken to complete one oscillation was always the same for a pendulum of a given length. 8.1.1, a simple pendulum. A simple pendulum consists of a small metallic ball called the bob of the pendulum suspended from a rigid structure by a long thread as shown in figure 8.7a. So this is the rigid support at the top, long thread and a bob. We did an activity in the chapter Measurement of Length and Motion in the grade 6 science textbook Curiosity, where we observed the oscillatory motion of an eraser hung with a thread. Is the pendulum similar to that? The pendulum at rest is in its mean position. When the bob of the pendulum is moved slightly to one side and released, it starts oscillatory motion. Its motion is periodic in nature because it repeats its part after a fixed interval of time. The pendulum is said to have completed one oscillation when its bob, starting from its mean position O, moves to extreme position A, changes direction and moves to another extreme position B, changes direction and comes back to O. Figure 8.7b. The pendulum also completes one oscillation when its bob moves from one extreme position A to another extreme position B and comes back to A. The time taken by the pendulum to complete one oscillation is called its time period. Let us now set up a pendulum and measure its time period. Activity 8.2. Let us experiment. Collect a piece of string around 150 centimeter long, a heavy metal ball with hook, a stone bob, a stop watch or a watch, and a ruler. Tie the bob at one end of the string. Fix the other end of the string to a rigid support such that the length of the string in between support and the bob is around 100 centimeter. Wait for the bob to come to rest. Your pendulum is now ready. Gently hold the bob, move it slightly to one side, and release it. Take care not to push the bob while releasing it and that the string is taut. Is your pendulum now oscillating? Using a watch, measure the time it takes for the pendulum to complete 10 oscillations. Record the time in table 8.1. Repeat this activity 3 to 4 times. Divide the time taken for 10 oscillations by 10 to calculate the time period of your pendulum. Note it down in table 8.1. So you need to record your observations here, and the length of the string has to be taken 100 centimeters. Is the time period of your pendulum almost the same every time? What do you conclude from this observation? The time period of the pendulum is almost the same every time. Think like a scientist. You just did an important historical experiment which was first done by Galileo. Except you used a watch to measure time in place of your pulse beat. Suppose you were Galileo experimenting with pendulums. What all would you investigate? What questions could you ask? What would all pendulums have the same time period? How would you test this? Repeat activity 8.2 using the same bob but with pendulums of 2 or 3 different lengths. Does the time period change? If so, how does the length affect it? If changing the length influences the time period, does the bob's mass also matter? Test this by repeating activity 8.2 with a fixed pendulum length but with bobs of different mass. Do you observe any change? The time period of a simple pendulum depends on its length but not on the bob's mass. All pendulums of the same length have the same time period at a given location. The time period of a simple pendulum of a given length is constant at a place. This property is used in the measurement of time. All clocks, old or modern, are based on some process repeating continuously, which can be used to mark equal intervals of time. Modern clocks measures time using the same basic principle, periodically repeating processes, but use tiny and very rapid vibrations either from a quartz clocks, or from some specific atoms, atomic clocks. While Huygens' early pendulum clocks could gain or lose 10 seconds each day, today's atomic clocks are so precise that they lose only 1 second in millions of years. Scientists are constantly searching for every even better ways to measure time with greater accuracy. So some common clocks and watches are being shown to you in figure 8.8. SI unit of time. The SI unit of time is the second. Its symbol is S. The larger units of time are minute, abbreviated as MIN, and R written as H. 60 seconds is equals to 1 minute and 60 minutes makes 1 hour. Dive deeper. Units of time such as second, minute, and hour begin with a lowercase letter. Except at the beginning of a sentence, their symbol S, MIN, and H are also written in lowercase letters and in singular. Note that a full stop is not written after the symbol except at the end of a sentence. While writing the time, always leave a gap between the number and the unit. Also note that writing SEC for second or HRS for hour is incorrect. Fascinating facts. The hole in the bowl of Gatika Yantra was made in such a manner that it took 24 minutes to fill and sing. The time unit measured by this clock was called Ghatika or Ghati. It became the standard unit of time measurement and continued until the end of the 19th century. A 24-hour long day was thus divided into 60 equal Ghatis. Activity 8.3. Let us identify. Look at the wall clock shown in figure 8.9 carefully. What is the smallest interval of time you can measure with it? 1 second is the smallest interval of time that we can measure using this clock. Science, and society. In today's world, measuring tiny fractions of a second is very important. For example, in sports, timekeeping devices can record events down to 100 or even 1000 of a second or a millisecond to determine the winners in a race. In medicine, heart monitors like electrocardiogram or ECG machines measures the millisecond variations in heartbeat to detect heart issues. In music, digital recording captures sound thousands of times per second for smooth playback. Many devices use even shorter intervals, smartphones, and the computer process signals in microseconds, 1 millionth of a second, allowing them to operate very fast. Scientists continue to develop even more precise time measuring tools for space exploration, medicine, and advanced science experiments. The faster and more accurate our clocks become, the more they help society in ways we may not even notice. For races covering the same distance, we can tell who was faster by measuring time. But how can we tell that when measuring races for different distances? 8.2. Slow or fast. What do we mean when we say something is moving fast or slow? Suppose you are watching a 100-meter race on a straight track. All the players begin from the starting line together, but after some time they are not running together. How do you decide who is running faster amongst them? Someone who is ahead of others at some instant of time is running faster than them. Hence, someone who has covered more distance within the same time is running faster. The distances moved by objects in a given interval of time decide which one is faster or slower. We often say that the faster runner has a higher speed. You are probably familiar with the word speed. So, speed can be defined by comparing the distances moved by two or more objects in a unit time. It can be found out which of them is moving faster. The unit time may be 1 second or 1 minute or 1 hour. We call the distance covered by an object in a unit time as the speed of the object. How can we determine the speed of an object? It can be calculated if we know the total distance covered by an object and the time taken to cover it. The speed of an object is the total distance covered divided by the total time taken to cover it. Thus, the speed is equals to total distance covered divided by total time taken. What would be the unit of speed? We know that the SI unit of length and time. Since the speed is distance per time, the SI unit of speed is meter per second and it is expressed as m slash s. Speed can also be expressed in other units. If we express the distance in kilometer and the time in hour, then the unit of speed will be kilometer per hour or km by h. A small numerical is given to you in which they have given Swati's school is 3.6 kilometer from her house. It took 15 minutes to reach her school riding on her bicycle. Calculate the speed. So here you will be converting the values kilometer into meters and minutes into seconds, and then you will be simply dividing the distance by the time, and your answer will be 4 meter per second. This is the simplest numerical on the speed. Activity 8.4. Look up at the railway timetable on the internet. Identify a train stopping at the railway station nearest to your place of stay. Find out the name of the next station where it this train stops. Also, find the distance to that station as given in the timetable. Note the time at which the train departs from your station and time taken by the train to cover the distance till the next station. So this line, I think, was skipped in between. Arrives at the next station, find the difference to calculate the time taken by the train to cover the distance till the next station. Calculate the speed of the train between the two stations and record it in table 8.2. Repeat for 4 to 5 different types of trains, passenger, express, or superfast. So you are required to note down your readings here. Compare the speeds of the trains, which is the fastest train. The train which has covered the maximum distance in unit time is the fastest train, that is the one with the highest speed. Relationship between speed, distance, and time. We know that speed is equals to total distance covered upon total time taken. So if the distance traveled and the time taken for it are known to us, we can write this equation in a different form to calculate the distance covered by an object. If we know its speed and the time taken by using total distance covered is equals to speed into total time taken. Similarly, we can also calculate the time an object will take to cover a distance if the distance and the speed are given by using total time taken is equals to total distance covered upon speed. So here in the question, Raghav is going to a neighboring city in a bus moving at a speed of 50 km per hour. If he takes him 2 hours to reach the city, how far is the city? So simply we are required to write on the values which are given. Speed is given, time is given, we need to calculate distance. So here the formula will become speed into time. Placing the values, you'll get the answer 100 kilometer. Next, a train is traveling at a speed of 90 km per hour. How much time will it take to cover the distance? So this time speed is given, distance is given. You are required to calculate the time. So time can be calculated as distance upon speed. Placing the values, you'll get the answer as 4 hours. Such type of questions you have already done in maths. In all the examples so far, we have found the speed of an object by using the total distance covered divided by the total time taken. However, the object might not have traveled the same speed during the entire duration of the time. The object might have sometimes moved slower or sometimes faster. So the speed that we have calculated is the average speed. But in this book, we have used the term speed for average speed. Science and society. Vehicles such as scooters, motorbikes, cars, and buses have an instrument which measures and displays the vehicle's speed in kilometer per hour. It is known as speedometer. Another instrument known as odometer is also fitted in the vehicles that measures the distance traveled by the vehicle in kilometer. I once watched a part of marathon on a straight road stretch. I noticed that some people seemed to be running at the same speed during that distance, while some people would speed up or slow down. How were their motion different? So motion is of two type. It could be uniform or non-uniform linear motion. Do you remember learning about linear motion in the chapter measurement of length and motion in grade 6 science textbook Curiosity? When an object moves along a straight line, its motion is called the linear motion. Now imagine a train on a track which is along a straight line between two adjacent railway stations. So the motion of the train between these two stations is an example of linear motion. The train starts from first station A at a low speed, then moves at a faster speed and then slows down and comes to a halt at the next station D. In between the two stations, for some distance, means from B to C, the train moves at a constant speed, that is, at an unchanging speed. An object moving along a straight line with a constant speed is known as uniform linear motion. So the train is in uniform motion between B and C. On the other hand, if the speed of an object moving along a straight line keeps changing, it is said to be as non-uniform linear motion. The motion of the train between A and B as well as between C and D is non-uniform. An object in uniform linear motion covers equal distance in equal intervals of time, while it covers unequal distances in equal intervals of times when it is non-uniform linear motion. In table 8.3, data are given for the distances traveled by two trains X and Y between the time 10 a.m. to 11 a.m. So you need to find it out which of the two trains is in uniform linear motion between 10 to 11 a.m. Train X covers equal distances in equal intervals of time, so it is uniform linear motion, while train Y is in non-uniform linear motion. Uniform linear motion is an idealization. In everyday life. We seldom find objects moving with a constant speed over long distances or for long intervals of time. That is why we have to use average speeds. So, this is the summary in the nutshell which is given to you. Once you are done with the reading, this is a numerical based chapter, and you should definitely practice the numericals that are given here. Here, you can pause the video and take a notebook in your hand and practice the numericals on speed and the uniform motion. These are easy ones. If you're done with this page, this is another page as well. Exploratory projects, in case you are inquisitive about science and are interested in making the projects, then there are few project based questions given to you. You can pause the video here, take a notebook, and you can practice. And here in the end, one question is there along with the fascinating facts. Time started when our universe was created and will continue in the future. We cannot see or feel time, but we can only measure its passage in terms of a time interval between events. These time intervals can be fractions of a second, or even days, or months, or years, or centuries. We can only say when an event occurred or for how long it lasted. Though we have learned to measure time with increasing accuracy and our lives are governed by watches and clocks, what is time continues to be a tricky question with no easy answer. So we are done with the reading of chapter number 8, and the name of the chapter was Measurement of Time and Motion. This is chapter number 8, taken from the Curiosity Book of Science, used for class 7, and it is suggested by NCRT. In case you are interested in hearing the audio of first 7 chapters, you can come to the playlist of my channel Online Biology Tutorials. Stay connected. See you in next live. Thank you for connecting.